Well, good morning, everyone. Thanks for coming in such a cold and snow day. And today I'm going to talk about week of symmetry and week of quantum double model. And this is a joint work with, Zhang and the Kaszlikowski and Chang based on this paper. And first of all, I want to emphasize that, this is one of the two learning projects. When I, during my last year at Purdue University as a PhD student, and I want to say that most of the idea in this paper are work from my co-authors, and so here's an overview of my talk. First, I will introduce the basic algebraic object in this talk, and then I will talk about the week of symmetry, which generalize some the Hopf symmetry. And as an example, I will introduce the week of quantum double model, and then we establish the gap boundary and domain work theorems of this model. Finally, we can use the tensor network state to give explicitly a ground state of this model. And so the motivations are as follows. The study of topologically all the phases of matter has attracted a considerable amount of attention during the past decades. And these topological quantum phases of matter usually have symmetry step beyond the Landau-Ginzburg symmetry breaking paradigms. So to understand this exotic quantum phases of matter, several kinds of generalized concepts of symmetry have been proposed, including higher form symmetry and non-invertible symmetry and categorical symmetry. Categorical symmetry is a promising framework to characterize the generalized phase transition, and the Hopf and Wyckoff algebra provide us with the general framework to understand symmetry. This notion of a Wyckoff algebra is proposed in such a way that the representation category of this algebra has a monadic structure, and in fact, it is shown that any finite monadic category can be realized as a representation category for some Wyckoff algebra. Therefore, a comprehensive investigation of Wyckoff symmetry will be, maybe helpful for us to understand the categorical symmetry. And finally, from the lattice perspective, the Wyckoff quantum double model are of their own interest. So, these are some motivations for us to carry out this work. So let's get started by introducing the Wyckoff algebra. We will work over the field of complex numbers. And first, a definition on weak by algebra. A weak by algebra is a quintuple consisting of a complex vector space W, which equipped with the following structures. An algebra structure with the product mu and units eta. And for convenience, we write the product as the symbol and the unit by 1 W. And sometimes we even just write as a 1 here. Second, a co-algebra structure with the co-product sub delta and co-unit. And if these two structures are compatible in the sense that the delta and epsilon are algebra morphisms, then we would get the notion of by algebra, but we will weaken these conditions that we only require that delta is multiplicative, preserving the products, and the units and co-units are weaker in the sense that the co-unit is weak multiplicative, where when you apply epsilon to 3 elements x, y, z, then you can separate the second element in the by these identities, where this notion I will introduce in the next slide using the co-product of the second component. And the unit is weak co-multiplicative in the sense that, well, you apply delta twice, then it is equals to the following complicated identity. So here are some notions that I will say. Delta is co-associative in the sense that you apply delta once and then you apply delta again to either factors, you will get the same thing. So we can denote either sides by delta 2, and this is a well-defined notion. Inductively, we can define, well, for k, for any integer k, we can define delta k in this by this formula. And the next, the second notion is the Sweater notation for coproducts, where we can just label a coproduct by, well, just write the first component by x curly bracket 1 and cancels with x curly bracket 2. And so inductively, we can write delta k as by this formula. It has, well, k plus 1 component in this case. And sometimes we can even drop the summation symbol for when dealing with the computation. This will simplify our notation. And so the weak Hopf algebra is defined as the following. It is a weak by algebra equipped with a linear morphism S from W to W, which is called the antipode. It satisfies antipodes and axiom as by these three identities. These identities are weaker than, well, the axiom satisfied by antipodes of a weak algebra. We can denote the result of the first identity by epsilon L, and we denote the result of the second identity by epsilon R. And these are linear maps between from W to itself, and we denote the image by WL and WR. These are called the left and right co-unital subalgebra of W, and they play the unit object in the representation category of W. So here are some remarks. First, for weak Hopf algebra W, the following are equivalent. First, W is a Hopf algebra, and then these conditions is equivalent to the, well, saying that delta is preserving the units. Recall that we have in the definition of weak by algebra only require delta to be preserving the product. This saying that delta is an algebra morphism. And second, epsilon is preserving the product, meaning that epsilon is an algebra morphism. And the last two conditions saying that in the case of Hopf algebra, the epsilon and epsilon are just equivalent to be, well, the co-units epsilon x up to a unit. So we can see that the weak Hopf algebra is just some kind of generalization of Hopf algebra. And we only consider finite dimensional algebras. In this case, well, the dual space of W is also a weak Hopf algebra with the structure morphisms induced by the canonical pairing between W and W hat. We can denote the dual by W check or W hat. And given an algebra W, we can define the W op as the opposite algebra equipped with this product by, well, using the original products and switch the two factors in here. And also, given a co-algebra, we can define the co-opposite co-algebra W cop equipped with a co-product that we switch then we swap the two components of the original products.
Sorry,
yes.
Remind that is the antipode as invertible?
The algebra?
Antipode as.
Yes. In the finite dimensional case, the antipode always the antipode is always invertible, but the order may not be 2 in this case. Compare the case to Hopf algebra, where the antipode always has an order 2.
In Hopf algebra?
Yeah, in infinite dimensional semi-simple Hopf algebra, the antipode is always has order 2, but in weak Hopf algebra, this may not be true anymore. Yeah. So more notations in this sense. For an element in W and phi in W check, you can define the arrows as the following. Well, these two arrows from left and from right will give the dual W check with a left W action and right W action. And this is the definition that these arrows will introduced by Swettler. And so the next task is to introduce the notion of quantum double of W. But first of all, we will form an algebra W check swap tensors with W. This is an algebra with the product given as the following. Note that we have omitted the summation symbol here. And also, the co-product of this sign is taken inside W check instead of W cop or W check cop. And it has the unit by, well, tensor the respective units in these two factors. And we can form a linear span J by those two elements. These are two, and this linear span is a two-sided ideals of this algebra. So the quantum double is formed by the quotient algebra by with this J. And definition, the quantum double of W is just the quotient algebra of this phi J equipped with the following Wyckoff algebra structure, where we can write down it very explicitly. And to prove this definition is well defined, it requires a considerable amount of calculations because because epsilon is not multiplicative anymore, and the unit has a non-trivial coproduct. So it will require a lot of computations in proving this definition. These methods are actually give the Wyckoff algebra structure on the quantum double. Anyway, the products in DW can be determined by the following called strengthening formulas, where the bullet is the argument of the function. And this formula is very useful when we give a representation of DW that we will see later. And in the following of the talk, we assume that W is a fixed finite dimensional C**Wyckoff algebra. So it is semi-simple because it's finite dimensional and C**. And the representation category, rep W, is the category whose objects are finite dimensional representations of W. It is a rigid monoidal category with unit objects given by the left per unit subalgebra, and whose action is given by this. Actually, there are other equivalent unit objects given by like WR. And we also have a similar equivalence of categories in the case of Hopf algebra. The quantum double DW has a quasi-triangular structure. So the representation category of this DW has a operating structure. And it can be shown that there is an equivalence between the general center of rep of W with the rep of DW as a very big tensor categories. Well, this is the proof. Well, mimics the proof that in the Hopf algebra case. So here's the end of the first part. And then we're gonna move to the second part that I will introduce the theory of Hopf symmetry. And in 2003, both Stroller and Slingerland proposed the notion of Hopf symmetry, where a state psi is called Hopf invariant if the action of an element on this psi is equivalent to, well, epsilon g times this psi. This will inspire us to introduce the following definition of Hopf symmetry. And for Hopf algebra W, a state where in some W module V is called left invariant under the action of G if the action of this psi is equivalent to the action of epsilon L of G on this psi. And similarly, for the left, a right invariant under action will be given by the right action of this element is equivalent to the action of epsilon R of G in this sense. And so, for a system with ground state psi, the Hopf symmetry of the system is the maximum Hopf subalgebra in the Hopf algebra W that leaves the psi invariant. So in this case, given such a ground state, we can form a space that generated by those elements G that act on this psi left invariant. In this such a Hopf subalgebra is unique by the maximality here. So we denote this algebra as the step W and psi.
So is it true that the overlap of
That's very true. Because those elements may not be from a Hopf subalgebra, but we just can form a maximum one that can generated by this element.
Okay, maybe I'll ask you later.
Okay. And so the basic physical data of a system are particle types, conjugation of particles, and the fusion between these particles. And the physical data are captured by the category of some some unitary categories. Where in our talk, I will use the category of rep W for some Hopf symmetry W. And more precisely, particle types are given by the equivalent classes of irreducible representations, where we can write such by a pair rho and M rho, where M rho is the corresponding module here. And the antiparticle are given by the dual of representations. And fusion rule is given by the fusion rule of the irreducible representations in this category. Then we can introduce the following definition. For fusion, anion model rep of W, a subset of the simple anions, A is called fusion closed if it is conjugate closed in a sense that if A in this set and then the conjugate, namely the dual, is also in A. And its tensor product closed, meaning that the non-trivial component of the fusion is also in this set. This is called a tensor product closed property. And so we have defined the fusion closed subset as in this sense. So in this time, we will generalize the result of Hopf symmetry breaking by and their co-authors to the Hopf symmetry case. And this is just very well kind of straightforward. But first, we can let's play with some linear algebra. Let F from W to V be a quotient map of Vygotsky algebras, meaning that F is a surjective map. Then the physical data of the V symmetry model are in one-to-one correspondence with the physical data of the W symmetry that factors over V. So more precisely, this saying that, well, for a particle A in the V symmetries, then there is a corresponding type AF defined by, well, they're defined with F with the same module, but the representation is given by the composition with F. And this corresponding preserves the irreducibility. Second, the corresponding preserves the conjugation of particles. Third, the correspondence preserves fusion rules. And finally, the last statement is from the first one, that if W is semi-simple and then V is also semi-simple. Yes, and well, this can be proved by simple linear algebra. And in a week of symmetric breaking, it's very important to determine that how to construct the subalgebra of a given week of algebra. So the a lemma saying that for a week of algebra W and a fusion closed set A, a linear space VA, which is generated by the matrix element of representations in A, is a weak Hopf semi-subalgebra in the dual we had. Note that this linear space is living in a dual space. This means that this linear space is closed under multiplication, co-closed under co-multiplication, and unclosed under antipode. So we can form, this space may not be a weak Hopf subalgebra, but we can take the minimum weak Hopf subalgebra in a dual that contains this space. So we denote this by VA tilde. Yes.
What is matrix elements of representations in A, or what is VA and as usual get?
Okay, so yes. So you have an so given such a representation, you will have a Morphin in here, right? Because M row is a finite dimensional vector space. Then for any element in here, you will get an endomorphism over M row, which by choosing a fixed basis in M row, you can identify this endomorphism in, well, GL in the matrix like M by N here. You fix a basis in M row. Then you get a matrix here, and then the matrix element is just a component in this matrix. Then this will actually a linear functions from W to C. So you can treat this as a linear function node, as an element in W. I mean, you can treat this as an element in the dual, and this will generate a linear space where we call A here, because it is determined by elements in a fusion closed set.
Okay, so but you in this lemma you fix the fusion closed set A. But in your blackboard, you just choose one particular representation, right?
Yeah, because I mean, well, A is the span by rho by J where X is in A and IJ is some indices in
Row, you mean row in
Row.
And I get. Thank you. So X is when you can leave X blank.
maybe.
Yeah, row is.
But how can we emphasize that row? Okay.
Row and I'm row.
Oh, yes. So this will live in the dual. Co-close under co-multiplication, meaning that, well, in the if an element is in this space and then you take the coproduct, the component in the coproduct is still in this space. Yes. By this, we can, well, generate a subalgebra as the proposition say here. Consider a finite dimensional system weak of algebra W, and if V is a weak of subalgebra, then we can prove that V is determined by a fusion closed subset A. In note that this A, the sum is in the is the irreducible of the dual. So meaning that, well, the process is that you give a weak of subalgebra, then this is given by, well, a fusion closed subalgebra living in W double check here. Because this A is in irrep of W dual, and because we are in the case of finite dimensional, so this double check is isomorphic to the original W here. So we actually did, well, show that how to define how to get the subalgebra of a given weak of algebra by a fusion closed subset in W check. And the second item is just a dual statement of the first one. So here's the main result in this part. In this part, consider a quantum phase C, which is just a wrap of W with Hopf symmetry W. And after the formation of condensate, the symmetry is broken into a weak Hopf subalgebra V, where so the new phase is given by the representation category of the subalgebra V. In this new phase, the particles can be divided into two parts, where the particles that have non-trivial monogamy with condensates are confined, meaning that a non-trivial monogamy, meaning that the double rating is not trivial. And the particle with the trivial monogamy with condensates are deconfined, meaning that they are free. They can well be moved to the phase, not in D here. And this deconfined particle will form a set A, D, C, which are fusion closed. So these deconfined particles are reducible representations of a new weak Hopf symmetry U, which is a weak Hopf quotient of V here. And well, it is kind of math to present this theorem here, and we can summarize by the following diagram. where well, this F1 and F2 are monoidal functions, and iota is an embedding of subalgebra, and pi is a quotient of equal subalgebra here. Yes. Well, can we move on to the next part?
So you talk about grading. So this we talk about was for the triangular, or you're talking about their common level.
Yeah. Well, we don't mention any grading not yet here, but as a concrete example, we will construct the quantum double model where the algebra is has a structure of quasi triangular, and so the category will be we have a grading.
But you mentioned monodromy.
Yes.
But it seems that
You are right. We should have written that this has a quasi-triangular structure in this algebra. Okay, but we miss this condition. Okay, thank you for putting out this point. And so let's move on to the next part that we will give an concrete example which exhibited some weak of symmetry well. So the setup is that we consider a lattice or graph embedded in some closed surface. And we fix a weak of algebra W, and then we form the total Hilbert space by, well, attach a space W to each edge as here. And for convenience, we consider the square lattice in here. And then we take a tensor product over all this space. So the total Hilbert space is tensor products over all the edges here. So this is the Hilbert space, and then we next task is to construct the Hamiltonian. First, we introduce some edge operators that from an edge. First, we can treat W as a left W module. For an element in here, we can define the L plus and L minus actions on W by using the multiplication in W. Note that we have used the invertibilities of the antipode here. And this will give two left actions on W. And also we can treat W as a left W hat module, where for an element in W hat, then we can define these two operations T plus and T minus by using the arrow notation that we have introduced before. And when we define the local operators, we need to engage some conventions for choosing the edge operators here. Like given an edge here, if we consider the vertex start from this edge, then we choose L minus. Otherwise, we choose L plus. And similarly, if the face is on the left-hand side of this edge, we choose T minus. Otherwise, we choose T plus here. So what does that mean? Let's see how to define or how to use this convention to define local operators. And a site is just a pair S equals to V and F, where F is a face and V is a vertex inside containing in this face. So like in here, this red bar represents a site here. So we have a vertex, we have a face. We use the bullet to denote this face, and then we have a vertex here. And it's a site. So given such a site, we can define the vertex operator and the face operator by the same philosophy. What I mean is that, well, the vertex operator only affects the edges around this vertex. First, we have a parameter from W, and then we label the edges around this vertex in a counterclockwise order, starting from this site. And then we use the coproduct of these parameters to use the corresponding component of the coproduct to act on the corresponding edges here by using the convention before. So like here, because this vertex is the starting point of this edge, so we use L minus C. And for this edge, because this vertex is the ending point of this edge, so we use L plus here. And for the face operator, the parameters come from the dual space W hat, and then we also order the edges around the face in a counterclockwise order, starting from the site, and then we use the coproduct of the parameters to act on the corresponding edges with the same convention before. So this is called the local operators, and they act as an identity for the other part of the lattice. So here's an example of the here are some example relations that satisfied by these operators. Well, the first identity, meaning that this operator will satisfy the will determine some kind of product in the quantum double that we have seen before. This is called the strengthening formula that we have seen before. And the second and the third identity saying that they satisfy the relation in the ideal J that we have seen before. So therefore, we can map, we can form a map from the quantum double to the endomorphism algebra of this HS. HS is formed by all the spaces around this site, meaning that, well, like if we have this is our site, so this H S will be the product of this U around well, which has some connect with the site by making from 5H to B5 times AH. So this will give a representation of the quantum double over this site. And so the construction of Hamiltonia requires some special elements that the high integral in the high integral in the we call subalgebra is an element H satisfying these three identities. Where, well, actually we have replaced the this is a kind of generalization of the high integral in Hopf algebra, but we replace the role of the co-units by epsilon L and epsilon R here. And for such a finite dimensional system of algebra, these elements always exist uniquely. So we denote it by HW. And because the dual is also a finite dimensional system of algebra, so its high integral is also existing uniquely. So we denote by cosine W of phi W. Because the high integral has some very nice properties, so we can form, well, we use for a given site, we use the high integral to define this A operator, because the high integral is co-commutative So we can see that this operator only depends on the vertex, not on the order of the labeling of the edges around the vertex. So we can denote this by AD. Also, when we use the parameters given by the high integral in W-check, then this also depends only on the face, not on the order, not on the whole sign. So we denote by BF. And again, because of the nice properties of the high integral, these operators are Hermitian projectors and commute with each other. So using these operators, we can form the Hamiltonian as the following, where we sum over all the vertex and over all the faces in the lattice. This is the Hamiltonian. Well, we actually just straightforwardly generalize the things in the Hopf algebra case, and nothing new here, but only the computation is more complicated than the Hopf algebra case. Yeah. So let's consider the ribbon operators in this case. Well, the building block of a ribbon is the triangles over on the lattice, like in here. These two examples of ribbons in the lattice. It consists of some consecutive triangles in here. And a triangle is just signified tau. It consists of an edge and two adjacent sides S0 and S1 here, where these two sides, the order of the sides indicates the direction of the triangle. And note that the direction of the triangle may not be the same as the direction of the edge. So we can use a plus or minus sign to indicate whether these two directions are the same or not. Okay. And well, these are two types of ribbon. And we define the type of ribbon as the one that consists of left-handed direct triangles. Well, what I mean is that when you walk along the positive direction of the ribbon, then the edges on the lattice always on your left-hand side. This is called a type A ribbon. Otherwise, you would call it the type B ribbon. Because in the Hopf algebra case, these two type ribbons will determine different ribbon operator algebra. So we can we need to treat them separately. But we will take the type B as an example to illustrate the construction. Well, the ribbon operators for type B ribbons are parameterized by elements in this algebra, the dual of this algebra. Note that this is the algebra that we have that we saw before, and it is denoted by F rho H phi. It acts on the total Hilbert space, but it only affects those spaces on the ribbons. And its definitions is defined inductively by the coproduct of this co-algebra. What I mean is that, to define the ribbon operators F H tensor rho, then we can decompose the ribbon into two parts. Like you decompose here, you get a rho 1 and rho 2 here. And then you use the co-product of these parameters. Then you use the first part to act on the first ribbon, and then you use the second part to act on the second ribbon. And because the co-product is co-associative, so this definition does not depend on the decomposition of the ribbon. So you decompose the ribbon smaller and smaller. Then you see the basic definition only relies on the triangle. So So the building blocks are triangles from the Riemann set, over which the Riemann operator is given by the H operator that we defined before. So for example, the Riemann showed in this slide, the Riemann operators act on this edge, and the definition is given by the formula. Well, so I will not give the definition of the Riemann, but it has a good property saying that for a Riemann with ending site at 0 and x1, and for such if the parameter is parameterized by the dual of the quantum double, then you will see that the Riemann operators will commute all the A and B operator in Hamiltonian where this site is not on the ending site of this Riemann. So this say that, so given a Riemann row here, and then this is the starting site and this is the ending site, and over all this Riemann, there are a lot of sites here, but the Riemann operator commute with all A and B operator except on the ending site here. This means that, well, this means that when you apply the Riemann operator to a ground state, then they will only create some excitations in both ending sides of the Riemann. This is the meaning of this proposition. So let me move on to the third part that we are going to say about something about the boundary theory. And for 2D topological phase with input fusion category C, the gap boundary theory is determined by a finite dimensional indecomposable module category over C. So the boundary excitations are given by the category of all C modules functors from M to itself. And this is a general theory. We will use these general things to study our concrete example. And for the bulk width of phase BW, we need to find an algebraic structure that fits into this formalism. One observation is that the gap boundary is characterized by a W comodule algebra A here. And the definition is, well, very standard. Let W be a weak Hopf algebra, and we say an algebra is called a right W comodule algebra if it has a coaction beta from A to agents W, such that this beta is compatible with the algebra structure on the two sides in the following sets. And so we can define the left comodule algebra by similarly. So the algebraic theory is that the gap boundary of a weak Hopf quantum double model, quantum double phase DW, are characterized by this W comodule algebra A. And the boundary excitators can be described by the category of I modules over A at A. So these are the general theory. And similarly, because the notion of model algebra and model algebra can be transformed to each other, so we can also describe the boundary by the W model algebras. And this is the general theory. And then next step is to give a lattice construction of this theory that we'll say here. And a few words about domain walls. Well, we can use the folding trick to say that a gap domain wall given by two weak Hopf algebra here, and we can transform the gap domain walls to a boundary. And conversely, a boundary can be treated as a special domain wall which you will face. So one can also establish the algebraic theory of domain walls with by commodal algebra as above. And then this algebraic theory match well with the correspondence given by the folding trick here. So let's see how to construct a lattice model of boundary. Let W be a weak Hopf algebra and A a right W commodal algebra. And we can write the coaction as the following: beta of x in as the x curly square bracket 0 times x square bracket 1. And this has the advantage that one can easily tell which element belongs to W and which one belongs to A, because those non-zero elements will belong to W and the zero label will belong to A. And of the lattice, well, at this time, the lattice will have a boundary here, and we need to orient the edges. But the direction on the boundary is not arbitrary, because we have chosen the right commodal algebra. So we need to assume that bar is always on the right hand side of the boundary when we walk along the direction of the boundary, and it's like shown here. So the total Hilbert space is that over the block we have the space W, and over the boundary we have the space of the commodal algebra in A here. So we need to define the local operators. Well, we need to introduce a boundary edge operator by a T tilde phi here using the coaction. Because this element belongs to W, we can evaluate this component by an element in the dual. So this notion is well defined. And for left commodal algebra, we can define T tilde minus similarly as before. So let's see how to construct the boundary operator. Well, the first case, the boundary face operator. Given a face near the boundary, we can define the boundary face operator using, well, actually the same convention as before, but in this time we use instead T tilde on the boundary, because this is not, because this because the space over this edge is the commodal algebra, not W anymore. So we need to engage what it, and well, this is similar to that case in as before. But a more complicated is the boundary vortex operator. At this time, the parameters is given by the algebra A tensor with A of. So given such an element, we can define the vertex operator A tensor B, and the definitions depend on the location of the site and depends on both the location of the site and also on the direction of this external edge. So there are 4 cases here, and we can write down very explicitly the definition, but it is not so important for this talk. So let's move on to the next slide. And the construction of the boundary Hamiltonian will engage some special element called symmetry, separability, idempotent. It is an element lambda. We write it as here, and it satisfies the following conditions. This is kind of generalization of the high integral, and for such finite dimensional semi-simple algebra over an algebraically closed field of characteristic 0, such an element always exists uniquely. And so using the linear extension, we can define the operator A lambda using linear extension. Then this will form the boundary Hamiltonian. And some remarks are here. Well, consider the special case. when A is given by a weak Hopf algebra. Okay. In a previous work, the boundary operator is given by, well, the this is the boundary. The boundary vertex operator is given by the R integral of the subalgebra. And in this work, we define the boundary vertex operator by the symmetric separability idempotent. And these elements in this case can be written down as the following. So you can see directly that these two operators are actually the same thing. And the second remark is just a rephrasing of the first remark in the case that group algebra. And so one thing is that for the group algebra case, the construction given here is will be reduced to the case that given by Beijing and their co-authors in 2011. So that's the end of this part. And then so let's see how to give some ground state of this model. Well, the building block is the weak of tensor traces. Given a pairing between two weak of algebra, J and W, the evaluation root can be described by this diagram. Like we can represent this pairing between these two elements by such a diagram. This is an edge, and you can see this is a face here. They have the same direction. And the reversion of the direction will engage applying the antipode here. So if you reverse the arrow here, you will get you will label this x by x of x. Also, if you reverse the direction over the face, then you apply the antipodes here. And the gluing are as follows. If there's an edge, if there are two faces sharing the same edge, then you can apply using the co-product of the edge elements to assign two components to the two faces like here. Also, if there are two edges on the same face, then you can apply the co-products of these face elements and then take the evaluation. So the Hopf tensor trace is given as follows. Given an oriented lattice, then the weak Hopf tensor trace is a linear function. Well, on each edge and on each face there will be some algebra labeling that face or edge, and then we assume that there are some pairing between adjacent lattice and between adjacent edges and faces. Then you can form for given a fixed labeling of the edge and labeling of the face, you can form such an evaluation using the definition in the previous slide. This will give you a complex number. So the corresponding state is defined by, well, you actually keep all the labeling on the edge, but you use the second component on the edge to form the coefficient with the face labeling, and then you keep the first component of the edge labeling in here, and this will give the corresponding state in this tensor network state. So to define a ground state, we need to keep a special labeling on the graph that we have seen. So given a lattice sigma is a closed surface, and C sigma is a given lattice, and we consider the quantum Hamilton the quantum double model given by a weak of algebra W. So we can assign each edge with the high integral of hw, and we assign the phase with the high integral phi w here, and then this labeling will give a ground state of the Hamiltonian that we have seen before. So this will give one of the ground state in terms of the weak of tensor network. And what about the boundary? Well, in a case that the cohomology algebra is given by a subalgebra, then we can form, well, on the back, we have the same labeling, but on the boundary, the edge on the boundary is labeled by the high integral of the subalgebra in here. So you can show that this is the ground state of the quantum double with boundary determined by this claim. And for a general cohomology algebra, we need to implement some additional requirement. We need to assume that this A is augmented in the sense that there is a multiplicated map epsilon from A to C, and for the symmetric separability idempotent, we need to define the element by using this epsilon to form this element. So in this case, the labeling of the boundary edge will be this element, replacing that high integral in HK. So this is the ground state of the boundary lattice model determined by A. And finally, well, let me make some summarize of the talk. Well, in a previous paper, we give a theory of boundary and domain wall of the Hopf quantum double, and we also in this talk we generalize the results to Wyckoff case. But there are also a lot of work to be done which I will present here, and this may be the future direction, but I'm not sure. So I'm gonna stop here. Thank you.
非常感谢唐先生的精彩报告，大家有什么问题？
I have a question.
Yes.
So you've mentioned, so like A be a cohomology algebra of W. I remember that you mentioned somewhere the bimodule of A, the category of bimodules of A, right?
Yes.
So is this bimodule the usual bimodule, or we have some compatibility with the action with W?
Yes. Yes.
The latter?
You mean it is usual same. We also require it is compatible with action of W.
有其他问题吗？我问一个问题，你这个算代数，你打算要做的是，就是说，如果这样出来的话，是 C 型代数还是冯诺代数？
C 型代数。
是 C 型代数。
嗯。
但冯诺代数不会出现吗？我一般物理里面其实出现的都是冯诺代数。你如果是 C 型代数的话，你这个 C 型代数都是什么样的 C 型代数？是 Euclidean 的，或是还是一些什么比较好一点的，或是 AF 代数，或是 AHF 代数，或是
我暂时不知道，但是那个现在目前的那个代数指的是那个那个 algebra。
它可以用主动的方式去逼近嘛？就是这种代数的话，
我还不知道。
完全就是说还是不知道它的结构是
吧？只有在那个就是在那个 infinity lattice 的时候，我们在那个 abelian 的 quantum double model 才可以就是那个由希望方子证明它既有某种 type， 好像是什么
三型的，
好像是这样的。
那是冯诺代数
啊。
如果是 C 型代数的话，没有这个 type。
那它现在目前只有在那个 abelian。
它无穷的话，
比如说
如果说它无穷的话，都是只还有单数。
因为目前我所知道。
因为这种 model 出来一般都是含单数的，就是冯 曼单词。
OK，
所以我就是比较好奇这边那个对应的这个理论是对应的双单数的哪些理论？
我还在学习当中。
非常好。没有问题的话，我们再次感谢同学们的参与。
OK，thank you very much.